I guess you folks had a long day. This is always very intense, and there are lots of events, lots of talks. So great that you come along and you still have energy in the evening. Okay, and we will not disappoint you. We tell you something that is going to revolutionize the way Earth data pixels get accessed, because it will become so much simpler that non-experts also can now get into this. That is the Earthserver Federation. Okay, so the program, we have an exciting lineup here after my intro, which will it will be followed by Chen-Yu Hao. Dr. Hao is actually deputy director of the GS data center in Taiwan, and he will dial in. I see him here already. Ni hao, great to have you with us. And so we have a truly international audience here and also presenters. Then technological perspective, Datacubes from a cloud operator's perspective. That is Yuri de la Mar from T-Systems. After that, we go into science and maritime science in particular with Dr. Tilman Dinter from Alfred Wegener Institute in Germany, talking about geospatial data infrastructures, specifically for the needs of that research center. Then Taras Matseliuk from OpNet in the Netherlands. I see that he is here as well. So we will see the industrial perspective of a startup that is developing innovative AI knowledge packs and combining them with data cubes. And finally, we step back a little bit and get a high-level overview on land governance and how that can be supported by Professor Fabio Terribile from Università di Napoli in Italy. So bear with us. We have an exciting program that shows data cubes from many perspectives and how they are influencing practice. And actually, data cubes, they are in everybody's mouth. We always were hoping that when we advocated data cubes in the first place, but it took quite some time until it lifted off, and now everybody is talking about data cubes. So data cubes give us analysis-ready data. What's next? Actually, in the first place, why do we want data cubes at all? Well, data cubes are simply a natural way for us humans to see data the way we perceive them anyway. I mean, if we talk about the atmosphere, if we talk about wind and rain, what do we have in mind? Something three-dimensional with X, Y, Z, or four-dimensional with X, Y, Z and time. So then, naturally, these data should be presented this way to humans. As it turns out, actually, that also makes it much simpler for tools to operate with. With the Earthserver project that started as a European-funded project in 2011, we have pioneered this. And so we can actually today homogenize data and this way make them better ready for analysis. So we have our RD data. In the Federation, we actually bring them together now in the next step. So we have them for analytics, for fusion, or simply for access if you want to get some parts of the data. And you will need to have subsets because we have dozens of petabytes available here in a totally location transparent manner. So all these data centers that contribute, actually, you just don't need to see where the data sit. You can combine them even if they're sitting in different data centers with no effort. That means coding free and based on open standards. This is open also for extension with other data, extension with code. Actually, we have several DSs on board. That is a growing list. And aside from that, we have data centers that offer specific data, like, for example, today, the maritime data we will hear about. This is an open, free, transparent, and democratic get together of institutions that retain full autonomy on their data. And it unites open and private data. So now you don't have to offer everything. It unites free and commercial offerings. And that is actually a quickly growing community. NASA is about to join, URAC is about to join, and we are talking to Taiwan about that and making plans. So actually, we have a growing critical mass of data ready for analytics for processing. The underlying Datacube engine is the Rasdaman Array DBMS, which offers distinct features, but I don't want to talk about technology today. Rather, from a user perspective, what are the key innovation components? Well, we have strictly standards that makes available powerful Datacube analytics based on WCPS and other standards, which are OGC standards, which are Inspire standards. The federation that I mentioned, so that we actually have one single information space, a planetary scale information space that is totally location transparent. The specific technology of an array database system gives us the power in the backend that ensures flexibility of any query anytime, that gives us scalability and support with many different techniques, of course, multi-core parallelization, of course, cloud processing and distributed processing, etc., while retaining full security about the pixels. By the way, benchmarks have reported performance superiority over stuff like, for example, ODC of up to 400 times. And this benchmark, just if you would think that we have done that, no. That benchmark that reported up to 400x speed up was not done by us in any way. The zero coding effort unleashes these for users that are no Python programmers, like it's advertised so often, like everybody on this planet would love to be a Python programmer. No, not really. Many are not. And so this leads to a democratization of data insight. And not the least, lots of different clients, because everybody has their favorite clients, their favorite tools, ranging from very simple, show me the data, up to high-end analytics and visualization. So that all comes together. And as I mentioned already, Rasdaman is behind Raster Data Manager, which actually has pioneered the concepts which you have heard so often this week. The approach is not a programming library. No, it's a query language, which actually meantime has become part of the ISO SQL standard under the name NDA. And we have a specific geo-coverage query language, which corresponds to the OGC standard WCPS. That is a full stack implementation, which is one reason why it's fast, which maintains today dozens of petabytes. We have parallelized single queries over more than 1,000 Amazon cloud nodes. And we have, well, the Earthserver Federation. For data providers, it's important that Datacube maintenance and optimization is fully automated. So you just can go and, well, have vacation on the Bahamas as an administrator. This is reference implementation for the respective standards, and, well, several innovation awards have acknowledged this. Okay, so distributed processing is where we actually take any incoming query and split that to distribute it in the cloud, to distribute it across data centers. And that is what makes the federation location transparent. By the way, yes, on a satellite we are. More about that later. Talking about projects, here is one example, big picture, where we have used WCPS to do a rule-based classification to find, in particular, in-field anomalies like frost and drought per field, per crop type. And we have done time series of Sentinel-2A, time series of Corinne, time series of soil data, and time series of climate water balance. And these in combination allow for a pretty accurate classification. Under the lead of Spatial Business Integration, an SME in Germany, actually that has been advanced to the state that this can be done in real time for regions and actually for the whole of Germany in 1 hour. Something completely different. You may not expect that, and it has nothing to do with satellite images. Telefonica has a series of 3-dimensional data cubes for radio networks planning. Actually, they have their complete mobile networks of Germany in there in the original ground resolution to do coverage analysis. And at some time, the marketing department discovered that, hey, these guys can do coverage maps. And so we used that. What you see on the right-hand side is a graphics that has been generated as a query. This is a query result done on original resolution on Datacube Fusion and then scaling it down so that now it's a graphics on the O2 website in Germany. So that was surprising for us, but we like the idea, of course. The big new topic, of course, is AI, in particular machine learning. And I believe now we can fulfill this promise of big data analytics better than ever. Big data, that is what the Datacubes contribute. Scalability, flexibility, federation, analysis-ready data, etc. On the analytics side, we find AI, which allows us to be flexible in training to different topics, to different questions, gives us enhanced insights, and large libraries of training data are available. So in the end, based on some, new technology that is currently under development in research projects, this will be easier, faster, and flexible for the users, in particular when it comes to digital twins, analysis, what-if scenarios, etc. So coming together, bringing together these different facets, the Datacubes are accepted as a cornerstone for analysis-ready data, but that is because they are single data cubes that are homogeneous. Yeah, within one data cube, you have one coordinate system, one resolution, etc. That is easy. But what about federations, where you have heterogeneous data cubes with different resolution, different coordinate systems, etc.? This is where Earthserver actually acts as an enabler, because you just don't need to care about that. You can bring them all together. In terms of data, we have a critical mass already. We have multi-dozens of petabytes. We have rich functionality built in, but it's extensible. So bring your own code, bring your own analysis. It's totally location transparent, making that easier, also with the open standards, and zero coding. So if you have data, why not join us? There's an advantage that every federation member advertises your data. Or if you just want to benefit from the data, join as well, approach me, and suddenly, well, life will be easier. That is our vision, to really democratize data to the extent that non-experts in AO, non-experts in Python can leverage, can benefit from the insights gained. So with that one, I would like to come back to the program. So I see how that you are online, and I'm really happy to welcome somebody who is now up and will tell us something at a really ugly time. So that must be a bad time for you, Hao. And I appreciate very much that you came along and tell us about the Federated National Datacube repository in Taiwan. So without further ado, please go ahead. The floor is yours.
Thank you for for inviting me here. Check.
So we still don't hear you.
Can you hear me now?
And now we see you. I mean your slides.
Yep, but can you hear me?
Audio is still missing. Maybe you have to unmute yourself.
No, I can hear.
I could hear. I could hear you.
For me, it's no problem.
Okay, so only Peter can't hear me. Okay, just make sure. Can you hear me, Peter?
Peter, can you hear us? Can you hear me? Hello, here's Tillmann from the Alfred Wegener Institute. I think Peter can't hear anybody.
Yeah, I think he has some connection.
Yeah, I can hear you too.
Maybe Veronica Kondo, who is the organizer, could help Peter to fix his audio problem.
I cannot do anything about his audio from here.
Yeah.
Okay, maybe you can proceed anyway. We try.
Okay. All right. So, hello everyone. I'm Hao from Taiwan, and it's almost 12 o'clock in night right now. So, uh, so still glad to be here to introduce about how we use the Rasdaman to build a federated national Datacube repository in Taiwan. And I'm going to share you with some real use cases and the progress of what we utilize this tool as the fundamental image database for sharing the Earth observation data as well as other coverage. Okay. Okay, so this is the background. Just same as a lot of other countries, we are also promoting the open government policy in Taiwan several years ago. And as you can see, we already got quite significant progress on the data set. However, based on the statistical number, we still lack of EO data set to be sure on this kind of proto, and also because of some characteristic of EO data, which also raise the difficulty to share it. And we did some evaluation about different platform and solutions. But as most of you are the expert of remote sensing or Earth observation field, I think you quite familiar with the EO data need large amount of storage and computing resource, and also the network resource to share those kind of data. So in Taiwan, we have tried the Google Earth engine, the Open Datacube, and Rasdaman in the past few years. And here's the development progress. We start trying the Open Datacube in 2017, and that's mostly collaborate with the National Space Organization and also the National Center for High Performance Computing. And also in the meantime, we involve Rasdaman as a alternative solution right now. The Rasdaman has become the official partner in NCHC, and also we from FCU we help NCHC to establish this platform based on Rasdaman, and also utilize the infrastructure that built by NCHC. We call TWCC. I'll introduce that later. And also, in the meantime, we are going. The next step will be try to make this data repository become national data national database, and with the federation capability, which can let the organization to share and to manage their data on this portal. Okay, so this is the basic architecture of the National Geodatabase, Geodata And as you can see, the infrastructure the infrastructure is established on TWCC, which is the Taiwan Computing Cloud, and managed by NCHC in Taiwan, and that's all managed. That's all based on different supercomputer infrastructure, and upon that, all different organizations they have their own Earth observation data or other coverage data. They can all rent resource from NCHC and put the image on the into the Rasdaman, and the different how to say the different virtual machine with Rasdaman, they can federate with each other through some OGC standards, and upon that, all the application can access to the national repository to retrieve the required image based on proof based on the proof, how to say, the proof accessibility. Okay, then for now we have finished the trial experiment. We built Rasdaman, and we already set up all the information control, the data sharing authorization, and also all the environment is built on a TWCC environment. And also we ingest various data like the NAT CDF, the NC file, the GeoTIFF with some Earth observation data, and also various web services already been published to different applications based on Rasdaman. And for now, we try to integrate various data sets to accomplish some kind of scenario. So today I'll bring you this agricultural scenario, and since we are in Taiwan, and I'm going to introduce a little bit about the environment of Taiwan. So we have only 1/4 area that's suitable for agriculture in Taiwan, because most of the area are mountain areas, you can see. And the average farm covers is only 1.1 hectare, which means all farms are very small, but and we have a large amount of farmers, and this make all the management and the information sharing become difficult between farmers and government agencies. And also we have we had a lot of serious disaster happens in Taiwan every year, and we have typhoon invasion, the earthquake, the flood, the drought, and also some wind invasions, and all these bring the difficulty to provide a stable agricultural environment. So as you can see, we have some political issues, and also the price of the fruit is quite sensitive due to policy issue, environmental issues, and once the sensitive fruit, the sensitive price on the fruit gets difficult or get down, all the farmers will require compensations from government, or they expect compensation from government, and that's why the government need to how to say, control or to uh, to know the situation of each farm or each area with the field or the fruit or the yield. And this is the cabbage cultivation monitoring in winter season. So as you can see, with time series image, we can find the different stage of cabbage, and also use the NDVI. We can estimate the time that and also the amount of the like the pineapple or some other sensitive agricultural yield. And but in traditional way, it's quite difficult for government to retrieve the data, to manage the data. So that's why we build this kind of system to help the agricultural authorities to manage their data. So all the data now they ingest into Rasdaman, and we provide a WebGIS based portal for them to calculate the NDVI, so they can easily to retrieve all the information from the image repository. And this is a very short demo that the user can select a bounding box with time period, and the system will retrieve all the list from Rasdaman, and all the information can be calculated or displayed as NDVI calculation result. And also, if you click the statistical button, all the NDVI distribution can be present based on the different time series image. And the other part is we try to integrate with Datacube and AI models, which means we trained a model to recognize specific field or yield. And as you can see in this demo, a user can select a area like the previous video, and he or she can view the image and click the analysis button. Then it can get the area distribution of the beetle nets. And for now we have the planet for beetle nut, for banana, the pineapple, and also the rice. And this is the last one. We also built a platform for NCHC to manage their image as a backend managed platform. So on this platform, the authorities can access to this system, and they can check all the coverage, and they can click the I'm sorry for the Mandarin. They can click the view data, then all the data can be seen on the WebGIS map directly, and this tool can help them to find the correct data more easier. And for now, we already contact and collaborate with several central government agencies, including the Agricultural Council, the Minister of Interior, and they all provide different kind of data. For example, the MOI, they provide a very high resolution DEM. And also for agricultural conceal, they provide the aerial photo with the entire Taiwan every year. And also they also took several Earth observation images. And also in NCHC, they put the land use, the DTM applications, and some simulation data. And also we collect the metro data from some university. And for the, as you can see, the blue cube means the demander, and the green cube means the data provider. So we try to connect a network which can let the local government, like the Taichung City and the Kaohsiung City, they can access to the federation network. Then through Rasdaman mechanism, they can easily retrieve the data from various cube if this cube has the data they request. And also in Kaohsiung City, we try to make the agricultural conceal as the data provider, and Kaohsiung City is the demander. And they all install Rasdaman in their own virtual machine. And we use Federation to connect these two agencies. So now the Kaohsiung City, they can access to they can get the data from the agricultural conceal in a very efficient way, and also they can overlay some DM on their website. And based on this architecture, we try to resolve the data silo and reduce the duplication of governmental investment. And because the analysis ready, and also the data accessibility, which we think can enhance the innovation on for the governmental agencies. Yeah. Okay, that's my presentation today. Thanks for listening, and let me know if you have any questions.
Excellent. Thank you very much. And once again, Dr. Hao, I much appreciate that you are coming at this ugly time to us to present. And I believe that was very interesting to see how that gets into practice and how Federation can be useful also locally. Okay, we are a little bit over time, so I hasten to move on to the T-Systems perspective to be presented by Yuri Delamar. And as we know, the telecom cloud operates the Mundi Dias, so we are talking about big data here, definitely. And I'm curious to hear your view, Yuri.
Yeah, thank you, Peter. So let me share my slides with you. So can you see that?
Yes, confirmed.
Thank you. Yeah, it's a pleasure to be here with you. My name is Yuri Delamar. I'm working for T-Systems, which is a large IT provider, part of Deutsche Telekom in Europe. We are very active, working for industry, of course, but also for many public sector organizations. In particular, of course, in this case, ESA, DLR, and also other space agencies where we have a long-term collaboration. For example, the Sentinel data from the start of the missions in 2012 were hosted for many years on our infrastructure, so that people on the internet could access them on the data hubs. Some of you will know them, to download and use the data actually from our infrastructure. So that explains a bit how we participate in Earth observation programs. Of course, as an infrastructure provider, you have a very different perspective. So, yeah, building on what Hao has shared with you in terms of very nice application examples and how this is being used for examples like agriculture in Taiwan, I wanted to give you a bit different perspective from a cloud operator, maybe giving answers to two questions. First of all, if you have seen what Taiwan is doing with Rasdaman, how could I use that if I do not maybe have this national infrastructure that I can use, or I'm just a startup company with a new idea and I want to see how I can make business out of this? What options do I have? And the second question is, what is the benefit of then using such a Datacube in a cloud environment? Yeah, what can I expect out of that? What type of benefits? So let me take you there. So first of all, what we do, as Peter has mentioned, is we operate since 2018 one of the so-called Copernicus DIAS platforms called Mundi Web Services. And in Mundi, we not only provide the Sentinel data, we also, of course, let people process the data directly in the cloud with all kinds of tools. For us, very important that people have a choice, that in the open source environment that we provide, they can do all kinds of things because our users come from very different domains with very different requirements. And here you see the marketplace that we have created for that. And on the marketplace, of course, the key tools that people use. I have made a selection of those in the menu that you can see. You can select then what you are looking for. And in terms of tools, you see in the middle of the page, you see Rasdaman as a Datacube analytics and fusion tool. So this is one of the key tools that we have made available on Mundi, knowing that Rasdaman has a very good community already. And this was a very important element also for us to show how things can be federated. Yeah, I think you have heard from Peter in his speech that Earthserver is not only a tool that can be implemented in any infrastructure like in our cloud, but once it is implemented, you can also then federate it with the other Earthserver implementations. That means for us a very important element, as we know that there is not one single platform today that can address all needs and all requirements of EO processing. For us, very important was the fact that with Earthserver, people can use what they already have, maybe available from other Earthserver implementations, and combine it with those that they then do on Mundi and do the analytics on, say, multiple data cubes if needed. So that is a very important feature that we also see coming in other directions and facilitates, of course, for users to really be able to access. So how do I access it? If I am like this startup company or a user that wants to first evaluate if this is really capable to address his analytics, well, very simple. We try to document very well, first of all, what can be done with the Rasdaman Datacube on the Mundi platform. You see here some of the information that we provide. Of course, there's a lot of documentation behind when you go into Sentinel-1, Sentinel-2, or the other sensors, what can be done with the data collections. So we try to make it very simple for the user, not expecting that they have a lot of background, like in science, but also want to learn how to use this type of professional analytics in a simple way, and also being able to get started within a couple of hours rather than days. Yeah, also very important to get new user communities attracted to these type of tools. So that is our goal, yeah, that with platforms like we run these on a cloud infrastructure, that it becomes very easy basically for everyone to get access to professional analytics tools and data cubes. That was the first question. The second question was, why would you run it, or why would you run such analytics in a cloud? What types of benefits would that bring me? Is the cloud not just another computer? In a way, yes, you could say that. But clouds, and especially the very professional cloud systems like we run it, based on OpenStack, that have many years of evolution and established processes behind and servers, it makes a difference. And that I wanted to show you in a bit different picture. Because when you run data cubes in a cloud, basically that is a whole bunch of processes, or what we say microservices nowadays, yeah, in a cloud. You run basically on demand, yeah, a lot of processes, and you want to run them as quickly as possible and as stable as possible. And that you can see very nicely from this top picture. This was not a picture from Rasdaman directly, as I did not have access to that information detail. But it's a very similar application that was used for physics data processing with some very similar analytics. And here you see what happens when you run, in this case, 250 containers or microservices in a cloud. Yeah, you can see that each line in this graphic represents one container. You can see really by the timeline close to midnight, yeah, that fully automated a new data cube, I would call it now, yeah, data cube process was started, yeah, by a machine, not by a person, because the person prepared it. That you can see by the first peak, yeah, around 7 o'clock in the evening, and then the system basically scaled up within seconds. Yeah, that's the first thing, that you can really switch on and switch off such clouds within seconds, just as we know it from a power grid, and that then the workloads can run very stable without any intervention. And that you can see especially from this very intriguing dip around 2 o'clock in the night, where some containers were losing connections. And then you see another very nice feature of clouds and running it in containers is that these can be self-healing. So you do not even need an operator or an intervention. If containers need to be restarted, this is also being handled by our cloud, completely automatic. And the processes can continue after that. And at the end of the run, that was in the morning, 7 o'clock, you also see that this is being done automatically within seconds when the job is finished. Say you have your results from your data cube, the data cube will automatically switch everything off, and you do not have any cost that continues. So you really also, like you probably know from clouds, you not only have a very stable operation, but you also really only pay for what you use. And it can be switched on and switched off within seconds. And how effective that is, because nowadays we also understand much more what is sustainability, what is green, and what is not green. And that's why I brought with me the other two slides, because it becomes ever more important that we do not only switch on and switch off computers or servers, but that we also understand, are these computers really running effectively? Are we using them 100% or 60% or 30% when they are switched on? And that you can see from the host load and from the Docker CPU percentage that you see in the bottom, where it's very clear that yes, especially in clouds where we can optimize this, every single CPU that is activated can be used to the 100% maximum level that they have available. So also in terms of sustainability, It's a very good model because we really use the available capacity to the absolute maximum. And that, of course, reduces the carbon footprint of running a process. So with that, I hope I've given you another interesting perspective of how Datacubes can be run and how effective and how sustainable that can be in the cloud. Thank you very much, and open for questions.
Thank you very much, Yuri Delamar from T-Systems. That was an interesting view from a side that looks, let us say, from the bottom up to the application and says what it can contribute. And I must also say, from our experience with the DIASs, one thing that we enjoyed is it simply worked. And that makes our life as software developers and software operators so much easier. Okay, unfortunately, in the attempt to catch up a little bit time, we don't have time for questions now, but I would encourage you to keep your questions towards the end, or you just put them in the chat where we can have discussion in parallel. But without further ado, I would like to go back into the scientific scene and welcome Dr. Tilman Dinter from Alfred Wegener Institute, who is going to tell us about ABI's framework on observation to analytics and archive. Tilman, the floor is yours.
Okay, one moment. I have to open here my application and so do you can see my screen now?
Yes, positive, we can.
Do you can see also the presentation mode?
Maybe you want to go into full screen mode? No, not yet.
Now?
We see the editing mode.
Okay.
Which means not the full slide, only the upper half of it.
Okay, then I will take this one. One moment. Okay. Then I will open it here. Okay, share my screen. So, one moment. Can you see now my screen?
Yes, much better now. Okay.
Excuse me. Okay, today I like to present our geospatial infrastructure, and I like to go a little bit more in detail how we implement this. And how we implement our geospatial infrastructure with regard to the new requirements of federation, and how we can share data, and how we can not only share data, we like to show we like to share also in our federation initiatives in the Helmholtz Gemeinschaft. We like to share also some kind of services and web services and so on. I start with our quite famous observation to archive framework. This is O2A framework. This is observation to analysis and archive. The Alfred Wegener Institute is an polar science institute which wrote and administrate thousands of instruments on the whole globe, and mainly in the Arctic regions, North Pole and South Pole. We administrate and we have many ships. The Polarstern is very famous. We have polar airplanes. We keep the station, the Neumeier station at the Antarctica, for example, and we have thousands of buoys in the in the ocean. And this is and all these data have to be centralized, processed, or some kind of ingested in our framework at the Alfred Wegener Computer Center. So we have all these data coming in, they are registered at Sensor, and here you see the different modules which is in the data flow, which you can see. And the data are ingested and they are registered in the sensor, and then we like to provide them to the users in workspaces and give them the functionalities of dashboards, analytics, portals, and in the end we like to archive the data in data repositories. I'd like to give now a little bit insights of our backend modules, and this is the geospatial data infrastructure, and this is the back end of these three modules I show here. This is the analytic platform portals where you can visualize data, where you can download data. This is the analytic module. This is more or less based on the Jupyter Hub or Jupyter Notebooks, where scientists are allowed to access directly data from the workspace. Workspace means some kind of virtual machine marketplace where we can deliver resources, IT resources to the users, and they can work then directly on this infrastructure. How our infrastructure, or as I said, the geospatial data infrastructure is built up. And not only built up, I want to show then how we realize the federation, the federated requirements with other institutes. Here you can see in a little small part of the framework I show before in the graphic. You can see on the left side the data acquisition, which have these different devices and and stations and so on, and they are ingested and laid down on our platforms, where we can where we store them intermediately, and they can also go directly with scripting ways, more or less, to archive them directly in our Pangea. This is our archiving system, but this is not only Pangea. We can also include here other storage possibilities. So I go further. Then we process the data somehow in a form that we can that we mark them as a geospatial data set and store them in a geospatial database. There can also come data from outside. This is not only our harvested or our measurement devices or our platforms. There also can be included data from outside. And this is going into our geodata server farm, I would say, which includes more or less 3 different server types, which are more or less the cores of this geodata infrastructure. This is an Argus server, where we store and provide data, sample data, sample data and scattered data, not rastered data. And we also have here the farm of GeoServer running, where we can react on WMS requests, where we deliver maps and tiles and images. And then we have as the third part, we have here the Rasdaman to deliver data and to answer requests of web coverage service and also web coverage processing services. This data, or this whole framework, or this whole farm, is now requesting or is answered requests on an OGC service based. That means that we have here standardized request, and the geodata farm is then, or the proxy is then delivered the special request which is coming to this backend, is delivering this to the Argus, GeoServer, Rasdaman, or something else, and is answering this request. You see that we also provide here a visual exploration framework. That means that that's a layer in between to the portals. The portals can be quite different. These are more or less visualization portals. This is, for example, marinedata.de or maps.rvde or some different kind of portals. This can be also some kind of local application. This can be in QGIS or in GIS application, which you are running local on your platform. Or this can also be, for example, which I showed, an analytics platform like Jupyter Hub or some kind of development environment you are using. So now this is the framework more or less inside the RV. Now we come to the aspects how we can share this data in this whole environment and the services we are like to deliver. For this, we implement now some kind of metadata service. This is based on a Surfcat implementation where we harvested our own server. We harvested our server and say, okay, which data are available, and please give me all metadata, and I store them in a metadata storage system. This is the Surfcat system, which then can be explored by the portal or the exploration framework. And this possibility gives us, or this gives us now the possibility to share this whole framework and this whole service functionality with other portals. So that you can see on the left side now, this is an external portal, and they are implemented in a different kind of way. Maybe this is maybe also a visual exploration framework, or and they have stored their own data in a geodata server, for example, and we are now able to harvest their geodata server and see, okay, which services or which data are you providing? Please give me the metadata, and we provide such a catalog over a REST API, for example. This is not the way we share the data. This is more or less how we share the catalog, metadata, and more or less which services are available. And so we can build up a network of different portals and different providers which provide maps and images. And now with the help of Rasdaman, we are able to share not only web coverage services or web mapping services. Now we can also share the whole world of the Earthserver Datacube Federation, where we can now also have directly access to data from the whole initiative which are involved in the Earthserver Datacube Federation with our Rasdaman, so we can directly access not only our own data, we can also have directly access to all other servers which are now directly connected to our Rasdaman server. And further, we can also, or we share also this data then, or the provided images or something, we provided them also as a direct web service to different external portals. Yeah, and here's now one last slide. This is an example of our Rasdaman server. Maybe you know this Peterscope web front end. And you can see that we have, for example, that we store nearly 12 terabytes of data locally. That's not too much, okay, but this is only the Rasdaman part. But we have also access to nearly 430 terabytes of data, which are provided by the Earthserver initiative. Okay, that's from my side. Thank you.
Tilman, thanks a lot for this overview, and you really managed to explain that architecture nicely, which involves quite a lot of components. Let me phase in briefly that, for example, a combination of GeoServer for the vector data and Rasdaman for the raster data is what I saw here on the diagrams, and which makes a lot of sense to me.
Yeah.
So, Tilman, thank you again. And going further to Taras Matseliuk from Opnet, a startup in Netherlands that has innovative ideas on how to deal with big data in an AI sense. And so, Taras, I would ask you on stage. I see you already. Please go ahead. The floor is yours.
Yes, hello, good evening, everyone. Let me start my sharing. So you should see the screen of a beautiful view from space of Hawaiian Islands, which should be replaced in a second with my slides.
Looks so much like vacation.
Yes, indeed. So let me move you guys here, and I'm ready. Welcome, everybody. I would like to greet you all and to say hello to everyone from Netherlands. I'm CEO and CTO of the Dutch startup Opnet. And before we dive into the topic of the new services which are becoming possible thanks to the Datacubes and AI developments, I would like to ask you a few questions which will help me to highlight the urgent need for this innovation. Because as you've seen, the previous presenters already achieved a lot with their current implementation. So why do we need innovation? Well, it is likely that many of you have PhDs in geosciences, right? But how many of you also have a PhD in data science? And how many of you also have a PhD in artificial intelligence? And now, if you have answered yes to previous questions, how many of you actually have more than 10 years of practical software development expertise? Please raise your hand in the chat. Anyone? Well, if you do, please contact me immediately because we are hiring usually superhumans with supernatural abilities right away. And this is basically the reason for the innovation that we are talking about. Jokes aside, the scarcity of multidisciplinary expert knowledge prevents rapid progress and inhibits our abilities to create new services for society, industry in general, and in particularly in the field of Earth observations and adjacent industries. This is why the Centurion Horizon 2020 project was proposed by our consortium, and it was recently funded by European Commission. Centurion project will create the novel platform for big data and AI technologies for Copernicus constellation of the Earth's remote sensing satellites, but not only. This project will take 3 years to complete, during which 10 European partners will work as a consortium on the technical management of Opnet and coordinated by the Inlicon group. To make the goals of to summarize, the main goals of this project are to make analysis of large Copernicus data volumes easy. Second, to make access and work with the platform easy for everyday scientists and developers. And three, in the process, we hope to open new market venues by lowering the barriers to entry and reduce the amount of effort required from different market players. And this project will demonstrate these ambitious goals in a set of specifically chosen use cases. So in order to create and deliver this demonstration use cases, the consortium gathered the multidisciplinary experts in the fields of geodata scientists and big data, AI and ICT platforms and delivery platforms, cloud service providers, and public communication specialists, as well as specific domain experts and scholars in the different areas of remote sensing. But most importantly, there were several thematic users interested in development of specific solutions in the targeted areas who have the practical interest in using of the developed use cases in the operational phase after the research phase of this project is complete. In addition, consortium will be guided by the space industry renowned leaders from KSAT and Airbus Defence and Space to ensure that the project remains on track and follows its original course. The project will consist of 3 technology enablers. So the first one is, of course, Datacubes. Multidimensional, we would like to call them data hypercubes, which extends the concept of analysis-ready data along further dimensions, which are particularly useful for the analysis of long time series from different heterogeneous sensors derived from diverse remote sensing platforms observing physically different properties, ranging from backscattering of electromagnetic waves and or in different bands, optical, radio, X-ray, potentially even muon in the future. AI knowledge packs is another enabler, which was pioneered by our company several years ago, represent the complex nonlinear programming structures with a deterministic approach to data analysis, consisting of refined data search and processing methods, combining different data sets, parameterization, generating metadata, creating models, and many other properties, joining all this in one compact structure. And finally, the pinnacle of the project will be the AI cubes, which we will create in order to scale processing capabilities or to the new heights by making the work of analysts making the analysis and work of scientists more efficient. So people don't have to know the coding, people don't have to know the IT structures. All we need is the domain and subject matter knowledge, and the system will assist in performing complex computational tasks. AI cubes will be programmatically accessible in addition to human natural language commands issued in written or spoken word English initially. So the proposed system architecture is displayed on this diagram. It depicts how the data from various sources will be accessed, transformed in the Centurion platform by its different components. The architecture is still being designed, and it's a future of the project, which is based on existing prior projects. And if you want to know more about our contribution, tomorrow I would like to invite you to another side event called Golden Eye, where we will conduct an in-depth dive into the components provided by OpNet to this project. But in the Centurion solution, we will take the existing concept to a new level. So, for example, we will be using the Rasdaman database for data access, storage, processing, and we will utilize the industry-leading Datacube database from them, which will be enhanced further in the scope of the project requirements. Federated access to existing data will be possible in Centurion, potentially creating a whole new market for enriched data analysis-ready data sets in the future. We will also mix and match AI Cube, which will enable a rapid and easy reuse of standard and novel data processing methods developed before and in the scope of the Centurion project, potentially creating the new market for analytical knowledge, which we currently know as AI knowledge packs, but it is only natural to expect that the industry will be adopting a better name such as AI cubes. The platform will also be accessible via standard APIs by the machine-to-machine clients, as well as with the natural human language instructions for easy visualization and for easy use by the human actors. So the analysis of the project will be demonstrated in the tailored 5 use cases, which range in the following areas. So the first use case will be focusing on generation of analysis-ready data cubes for a very large geographical areas. In this case, we plan to cover more than 1 million square kilometers, combining different data sets. For example, Sentinel-1 interferometry suitable data with optical and multispectral data from Copernicus satellites. Then these data sets could be used for thematical use cases. And in this case, we will have agricultural weather index case, which we will perform together with Julius Kühn Institute, which will be generating agricultural weather indexes for entire Germany for years in the scope of this project. The third use case will be focusing on maritime area, where we will be using the same platform for studying and analyzing the North Sea shipping dynamics on a daily basis, if possible. All depends on the data that we will be receiving from satellite and ability for us to access not only the Sentinel-1 data, but also data from the contributing missions in the scope of this project, especially commercial missions like TerraSAR and ICEYE. Fourth use case will focus on the near real-time force dynamics monitoring. And we will be performing it together with WSL from Switzerland, who is part of the consortium. And the final use case is near real-time mapping and attribution of natural disasters, which we plan to present results to the Copernicus Emergency Management Services in hopes that this novel platform could be utilized by Copernicus services themselves in the future as a demonstration. Well, on this, I would like to conclude the presentation about this exciting project, which is going to be keeping us for the next 3 years. And also I would like to use this opportunity to invite those participants who are interested to benefit from the platforms, either by receiving results of the depicted use cases, or even actively participating as the stakeholder by joining the ecosystem, by joining our so-called Helix platform, which is a special crowd collaboration platform provided by one of our public communication partners. And I encourage you to click or scan this QR code to give us the answers for our survey, where we collect user requirements and refining the stakeholder needs in preparation for the refinement of the architecture and deployment of the platform. By the way, this platform is scheduled to be in prototype stage, deployed by the end of the year. So monitor this space, subscribe, and follow us. Thank you very much.
Thank you, Taras. That was a great overview. And what I like very much about this project is that the different communities come together and do their science and their societal use cases and make use of the technology in a joint manner. So thank you again. And now for the last one, Hawaii, okay. Why don't we have our next meeting there? So
how do I stop it?
I'm simply taking away and getting over to our next speaker. Let me briefly show you something. So actually, you are looking now into the Mundi dashboard to the Sentinel data, but as we have emphasized so often today, this is federated. And here you are looking at data that are sitting actually at the Napoli University, which is where our next speaker comes from. They are tremendously active in building up all sorts of data. And as you can see, alone here, these data that we see listed is more than 800 data cubes of about 23 terabyte altogether, which sit here in the listing. And if you remove it, you see the full thing again. So I'm very happy that we could win Professor Fabio Terribile, who is leading an initiative towards integrated land decision support, and who is wrapping up this view, complementing this view from cloud provider to software developer to users, now from a high-level political perspective, to show us finally the big picture. Fabio, thanks for having you, and please go ahead.
Thank you, Peter. Can you hear me?
Yes, loud and clear.
Okay, perfect. Of course, thank you for this opportunity. It's yes, I'm happy to be here. I will time myself to be, because we are all tired, I think, after this intensive day. So basically, I coordinate this Horizon 2020 project that I collaborate with also with Peter, who is here. But it's about developing a decision support system based on land and through this is done coordinated by this research center, which has a strong focus on the geospatial decision support system, basically. So a few words about myself. I'm not an IT person. So I'm basically a pedologist, a person working on soil, on ecosystem services produced by soils and land degradation processes that unfortunately are, of course, creating lots of problems in all the world on our soils. So this is just to give the upbringing. So why a person like me develops such type of project on the decision support system, which, as you will see, has a very strong IT component. So let me give just a few basics. Producing data is our job and is obviously extremely important. So all of us, of course, are involved in processing satellite data, or as we also collecting soil, maybe making measurements, and of course, we are all also engaged in different types of artificial intelligence and so forth, so on. So we are all very much in this effort, and ESA is, of course, very active to that respect. Nowadays, we really realized that we have huge agriculture environmental challenges. Many of those are extremely complex, and the only production of data, even when you combine with beautiful visualization or sometimes pre-operational services, sometimes are just simply not enough for the complexity. Very few think about the use of data. Many administration, for instance, if I think region, even ministry or things, sometimes you have a beautiful experience. We just heard the one of Taiwan, but generally the use of data are much lower. And so there is really a gap here in between. Of course, there are different ways to try to fill this gap, maybe to form this guy to get there, but we chose different things, because in real life you have to produce things which makes the life easier to the people. And so this project goes there, attempting to produce decision support tools for many things. So the things are rather complex. Here I put a series of policies we impact on with our tools. I shall demonstrate in a moment. And you see that many of these things, imagine the nitrate directives, for instance, in the European Union, varies every day on the base of rainfall, how much nitrate is going towards the groundwater, so it's strongly dynamic, and varying the landscape because different soils have different attitude. So many of these laws are actually have inherited complexity that often we underestimate. So this is, I will jump directly. So then if I say life is complex, we require engine to address such complexity and not to oversimplify complexity. So the project goes there. This is our web page, www.land-support, and it's a project which will land in April 2022. We are a really large number of people and attempting to do these three major things: to produce tools to support agriculture and forestry, to support sustainable spatial planning, and to help the implementation of series of policies. We work at very different scales: Europe, nations, some regions, and as you see, Rasdaman is here. But what was important is to show that we have also some public authorities, not only scientists, research bodies, but 5 public authorities at a different scale. Basically, our architecture is this one. You see vector data, raster data, and raster data. Of course, you see Rasdaman, and we are really attempting also to address this Earthserver Federation-like system. So this is, but we are not just visualizing this data. For us, it's crucial to apply modeling engine on this data in order to face many applications. Some of these modeling are static, some dynamic, some are very simple, some are rather complex. but all this complexity is hidden to the user. When I say complex, means also maybe lots of differential equation to be done on a very large amount of soils, for instance, to understand the water balance of different soils in different parts of the landscape. So it's not surprise to you that we use also lots of parallel processing on Rasdaman, but also on other type of data. And then, of course, graphical user-generated map, tables, PDF, etc. So I will use, these are just some crucial things we have. We have a strong emphasis on deterministic central engine, stronger modular structure, an emphasis, of course, on validation, the large use of data cubes and GPU and comps on CPU-based parallel processing, and a series of other things. So the tools we produced are basically, as I said, different region, but you see once you have this beautiful Rasdaman Datacube and also this modeling, etc., you do realize that you can create synergies. So if you produce a water balance for a soil, which is very heavy, you can use that type of information for many different things. So it does not surprise very much that we produce completely different tools, some from agriculture, forestry, environmental protection, land take and spatial planning, and even biodiversity and ecotourism. Of course, some refers to regional scale, some to national scale, and some even European scale. So I want to take just 2 minutes to jump to another presentation, if I can, that basically to give you an overview how a system like this can work. This is our type of platform. I will just show to you the land take. Why land take tool? Because we have by 2050 in all Europe to reach zero net land take. So it's a specific regulation. So we produce a system which is the only one existing for entire Europe to better mitigate land take at any municipalities, province, regional level. So that's the system. This is, for instance, you see here already a series of tools that you can click. Some maybe just produce a report. For instance, this is a report of the municipalities with information on water bodies, population, etc., etc. And or you can produce on the fly. This is on GPU processing, some fragmentation map, a map which basically tells you, which of course analyze data from Rasdaman and evaluate how much the rural landscape is fragmented by the urban areas. And this is very useful to decide where to put new urban development or hopefully new green corridor. So it's, and you can decide on the fly, for instance, some parameter, this is very important, which is the width in which you basically, you run your algorithm. Just an idea of some parameter, this is edge density, some metrics. You can get graphs of many metrics related with this item. And all these are typical index used by spatial planners. And of course, you could also, I will jump at the last one, which is this land take monitoring. Basically, you can query your Datacube and obtain between any 2 dates how much your maps, where is the new building between the 2 dates, but also most importantly, the quality of soils you have lost in your, for instance, planning. So this brings me, I stop because I almost reached the 10 minutes with some very small conclusion. And this is just to say that we have to think bigger. Also in other Datacube, applying modeling on Datacube to produce real tools. There is a real game that not everybody realized that we have a little in terms of supporting decision. And So we must create something more complex if we have to face many of our environmental challenges of nowadays. And so we need, of course, to address multifunctionality of soil landscape. We need to, of course, have tools adapted to the need of user, and that's very important to have a modeling engine which enables what-if questions, scenario analysis, because this is very much important. And of course, the system can enable also bottom-up contribution, is user-friendly, but this is, of course, as a cost. Imagine for us working on soil to be engaged in such IT items, but we must somehow abandon our certainties to face this big game. So thank you very much, Peter. I take 1 minute more, but I think I stop here.
That is perfectly fine. And actually, you even saved some time. So, Fabio, thank you very much for this high-level overview perspective that shows how governance at large can benefit. And with that, actually, we are at the end of our small excursion into the Earthserver landscape. So give me a second. Okay, that is what we have seen today. We have looked from the hardware and the cloud perspective over the software perspective into applications, up into governance. And we hope that we gave you some composition of talks that help you to see where there is benefits, and maybe there is also a benefit for yourself, for your institution, or for your future projects. If you want to know more, please feel free to talk to me. I'm just putting my email address into the chat here so that we can stay in contact. And I would appreciate that, actually. And therefore, let us now enjoy. Hey, we have reached the evening, and maybe you raise a glass of wine in Frascati, or you stay at home and relax now. Thank you very much for bearing with us. We're wishing you a great Phiweek, and on this occasion, big thank you also to Isa for organizing this get together, which is always again interesting, and there is something new to learn. So thanks everybody. Have a nice evening, and bye-bye.
Thank you, Peter. Bye.
Thank you, Peter.